Hello. Yeah, welcome back. This is the demo that I was talking about. So the interface that you're seeing is what is called as a Python notebook, IPython notebook. So it is done using Jupyter and in Anaconda platform. We will share the details. When we will post this on GitHub, you'll be able to download it and actually run it if you're interested. So this particular thing is actually showing you how the wave functions are calculated. Sorry, let me do this. So the wave functions are calculated for finite and infinite potential wells. Okay, this is taken from this paper basically. It's by Cernek and others. Basically, it's called a Python program for solving Schrodinger equation. The reference is provided and the link is there. So you can actually go through it. It has a lot of interesting things that we were talking about. So this details will be useful for a master's level student. I just wanted to add it just to make it complete. Okay. For an undergraduate student, I don't think you need to understand what is there, how the code is done. You just can observe what is happening. So here, what we're doing is we're taking a potential well. The details are all hidden from you. Okay, you don't have to worry about it. So what we're doing is we represented this potential well, right, of a certain width, and there are certain energies. Okay, so we saw that the width is in the denominator, L square is in the denominator. So what happens if I increase my width, right? So if you look at, these are some numbers, basically arbitrary units. So right now the width is 3 and n is 4. N is basically the number of eigenstates allowed. So calculated, okay? So 1, 2, 3, 4. You can actually calculate more eigenstates, there's no problem, okay? This is an infinite potential well. We cannot show infinity in a graph, but it goes up, right? So as you increase the number of energies, you can get more and more, of these things. Okay, wave functions. So you see the wave functions, the first 3 wave functions if you see, they are exactly what we said they will be, right? Like a sine, half wavelength, a full sine, and then this is the third state and so on. And the energy, for example, let's take the reference of 4.9 EV, right? Let's say it's EV, arbitrary, 4.95, okay? So right now it is 5, the topmost state, okay? So you will be able to actually play around on your own and analyze it, okay? That's why we want to post it, okay? Okay. So now if I decrease my width, what happens? Energy should increase. And that's exactly what you see. From 5, it became 11, okay? And if you increase the width, it should become lower energy, all right? And you could actually compute these energies. What is the difference in energy 1 to 2? If there is what is the difference in energy? Okay, just like we mentioned the absorption, right? You can have an absorption from first level to second level and all that. You can compute these things. Okay, this is basically the infinite potential well, and we have also done this for a finite potential well. Finite potential well means there is a certain depth you can mention, right? And so in this case, we saw that, let's just take, 2 wave functions. Well, this is not wave function, number is not there. So basically A is basically width of the well and D is the potential depth, okay? So let's say if I have the depth as 30, okay? It's arbitrary units, let's take it as EV anyway, okay? So now as I increase, you see that there are these wave functions and the topmost wave function is actually penetrating into the barrier, just as we showed in the graphs, okay? So you can play around with this. Let's say I reduce my width. Okay, what happens? What would you expect if the width reduces? Okay, I would say that there will be more penetration. And you see this? The cyan, the bluish color is actually penetrating more into the barrier. Okay, or you come back and then now you say that I'll actually increase the width. When you increase it, of course, there are more levels which are showing up, and then there is less penetration into the barrier. Similarly, the depth will change. If you decrease the depth, there will be more penetration. Okay, let's go back to 2 here. So it's penetrating more, but if you increase the depth, for the corresponding energy, it will be actually deeper into the well, and it will not penetrate that much. Okay. So there are all kinds of interesting things. If some of you are interested in having deeper, if you want to work deeper into these areas and want to do research or something, you could always email me. Okay. We'll talk about it. We can do a small project based on some of these things, and we can actually do more work. Okay. All right. There is also a small self-assessment quiz which we added into this. So you just have to run this once, and you will have options. Basically, eigen energies of an electron in infinite well are continuous, discrete, and insufficient. You could simply submit a cross-check for yourself. Okay, is it continuous? No, right? Eigen energies of electron in infinite well are discrete. They are not continuous, right? That's what we said. Similarly, some simple things. These are not really complicated questions, but it will give you, eigenfunctions penetrate outside the walls of an infinite well. Will they? Of course not, right? They don't. Only for a finite well they penetrate. So some simple, just sanity checks for you. So this is the short demo that I wanted to do, and I'll put it on GitHub. It will be an open resource, a GitHub repository which you can use and download. We will also add a note on how to run it. Okay. All right. If you guys are interested in coding, you could check it out. All right. Okay. Thank you so much. We will meet you next week.